Welcome to the presentation of global processing via the Huff transform. Global processing via the Huff transform. Given n points in an image, suppose that we want to find subsets of these points that lie on straight lines. Huff in 1962 proposed an approach commonly referred to as the Huff transform. Consider a point xi, yi and the general equation of a straight line in slope-intercept form, that is yi is equal to axi plus b. Infinitely many lines pass through xi, yi, but they all satisfy the equation yi is equal to axi plus b for varying values of a and b. However, writing this equation as b is equal to minus xia plus yi and considering the AB plane, also called parameter space, yields the equation of a single line for a fixed pair xi, yi. Furthermore, a second point xj, yj also has a line in parameter space associated with it, and this line intersects the line associated with xi, yi at a dash b dash, where a dash is the slope and b dash is the intercept of the line containing both xi, yi and xj, yj in the xy plane. In fact, all points contained on this line have lines in parameter space that intersect at a dash b dash. These figures illustrates the concepts. Figure 1 shows the xy plane. Figure 2 shows the parameter space. Huff transform subdivides the parameter space into accumulator cells as shown here in figure 3. The computational attractiveness of the Huff transform arises from subdividing the parameter space into so-called accumulator cells as illustrated in figure 3, where A max A min and B max B min are the expected ranges of slope and intercept values. The cell at coordinates ij with accumulator value aij corresponds to the square associated with parameter space coordinates aibj. Initially, these cells are set to 0. Then, for every point xk, yk in the image plane, we let the parameter a equal to each of the allowed subdivision values on the a-axis and solve for the corresponding b using the equation b is equal to minus xka plus yk. The resulting b's are then rounded off to the nearest allowed value in the b-axis. If the choice of AP results in solution BQ, we let A of PQ is equal to APQ plus 1. At the end of this procedure, a value of Q in Aij corresponds to Q points in the xy plane lying on the line y is equal to Aix plus Bj. The number of subdivisions in the AB plane determines the accuracy of the collinearity of these points. Note that subdividing the a-axis into k increments gives, for every point xkyk, k values of b corresponding to the k possible values of a. A problem with using the equation y is equal to ax plus b to represent a line is that the slope approaches infinity as the line approaches the vertical. One way around this difficulty is to use the normal representation of line, that is x cos theta plus y sin theta is equal to rho. Figure 4 illustrates the geometrical interpretation of the parameters used in the above equation. With reference to figure 4a, a horizontal line has theta is equal to 0 degree with rho being equal to the positive x-intercept. Similarly, a vertical line has theta equal to 90 degree with rho being equal to the positive y-intercept, or theta is equal to minus 90 degree with rho being equal to the negative y-intercept. The edge linking problem based on the Hopf transform is as follows. Number 1. Compute the gradient of an image and threshold it to obtain a binary image. Number 2. Specify subdivisions in rho theta plane. Next, number 3. Examine the counts of the accumulator cells for high pixel concentrations. And number 4, examine the relationship, that is principally for continuity, between pixels in chosen cell. The concept of continuity in this case usually is based on computing the distance between disconnected pixels identified during traversal of the set of pixels corresponding to a given accumulator cell. A gap at any point is significant if the distance between that point and its closest neighbor exceeds a certain threshold. Here is the end of this presentation. Thank you.